You know what it feels like to be heavy. Right now, as you sit wherever you are, gravity is pushing you down. Your body weighs exactly what it weighs. You can feel it in your bones, in the weight of your head against your shoulders. It's constant. It's boring. It's so ordinary that you don't think about it anymore. But once, there was a star. A massive star. Dozens of times heavier than our Sunday. And that star lived for millions of years, burning hydrogen in its core, expanding and contracting, following the rhythm that all stars follow. Then, one day, it died. When a star dies, what's left behind falls inward. All of it. All that mass, all that weight, collapses down to something impossibly small. And when that collapse reaches a certain point, something strange happens. The gravity becomes so intense that nothing can escape from it. Not light. Not anything. A black hole forms. But this story isn't about a black hole destroying something. It's about something that refused to die. Near the edge of a black hole called V404 Cygni, there is a neutron star. And this neutron star is not alone. It is being pulled toward the black hole by gravity relentlessly, constantly, like a rope that never loosens. The black hole is stealing material from the neutron star, pulling it away, shredding it. You might think that means the neutron star is disappearing, that it's being torn apart. But the neutron star is not disappearing. It's still there. It still has mass. It still has weight. And it's being crushed into something even denser, even more impossible than before. This is a story about what happens when one of the universe's most extreme objects meets something even more extreme. It's a story about survival at the edge of the abyss. It's a story about matter and gravity and the deepest mysteries of how the universe actually works. But before we can understand what's happening to this neutron star, we need to understand something simpler first. What does weight actually mean? Right now, the planet beneath your feet is pulling you down with a force. That force has a name: gravity. Everything pulls on everything else with gravity. You're pulling on the Earth right now, just as hard as the Earth is pulling on you. The only reason you can't feel it is because you're so much smaller. Your gravity is so weak it's almost nothing. But that's the thing about mass. It doesn't just pull on things. It warps space itself. It bends reality. And when you have enough mass in one place, when you have really, truly enough of it, something breaks. The heavier something is, the more it warps space around it. A star warps space a little bit. A neutron star warps it a lot. A black hole warps it so completely that space itself becomes a trap. And right now, at the edge of a black hole, a neutron star is being pulled deeper into that warped space. The density is increasing. The gravity is getting stronger. And something is happening that almost no one has ever understood until very recently. The neutron star is not being destroyed. It's being reborn. Let's start with something you can touch. Take a piece of iron, real iron, the kind you can hold in your hand. It's heavy. A single cubic centimeter of iron about the size of a dice weighs about 8 grams. That's roughly the weight of 3 sugar cubes. Iron is made of atoms. Those atoms have nuclei at the center, and electrons orbiting around them, just like planets around a star. Most of iron is empty space. If you could somehow squeeze out all that empty space, if you could push the nuclei and electrons together until they were as close as they could possibly be, iron would be much, much denser. But we can't do that. The forces holding atoms apart are too strong. Nature can do it, though. When a star about 20 times heavier than our sun reaches the end of its life, it does something violent. It explodes. The explosion is so powerful that it shakes the star apart. But at the very center, something survives. The core of the star doesn't explode. Instead, it collapses. All of that mass, all of that weight, falls inward in less than a second. Electrons are forced into protons. The nuclei themselves start to touch. They begin to merge. And in the end, What remains is something that has never existed in your entire experience of the universe. A neutron star. A single teaspoon of neutron star material would weigh as much as all the cars on Earth combined. Let that land for a moment. A teaspoon. Not a cup, not a bucket. A teaspoon. All the cars. All the vehicles on every road, every parking lot, every highway on the entire planet. In a spoon. But that's still not the densest thing in the universe. A black hole forms when something is even heavier than a neutron star, or when a neutron star is compressed even further. At the center of a black hole, gravity becomes infinite. The very concept of space and time breaks down. Physicists have only theoretical equations to describe what happens there. No one has ever actually seen inside one. Now imagine a neutron star, something so dense that a teaspoon of it weighs more than all the cars on Earth being pulled into orbit around a black hole. This is where V404 Cygni exists. V404 Cygni is a binary system. That means two objects orbiting each other. One of them is the black hole. The other is a companion star, a normal star, like our sun but different, feeding material to the black hole and to the neutron star that orbits between them. The gravity here is not just strong. It's fractured, torn. Multiple sources of gravitational pull are fighting over the same material. The neutron star is being stretched. It's being heated. Material is being ripped away from its surface and funneled toward the black hole. And this is where something remarkable happens. The neutron star is so dense, so compressed, that it doesn't tear apart. Instead, the material being pulled from it falls toward the black hole. But before it disappears, something else happens. The black hole's gravity is so intense that it pulls this material into a spiral. The material heats up, it accelerates, and then just before it crosses the event horizon, the point of no return, the black hole's gravity becomes so extreme that it forms what's called an accretion disk. An accretion disk is what happens when material spirals into a black hole. It's not a smooth fall. It's a violent, heated spiral. The material compresses, it heats. The friction between particles creates temperatures of millions of degrees, and the neutron star sits at the edge of this, being crushed by gravity on one side and bombarded by intense radiation and material on the other. The neutron star's surface is being stripped away. Layer by layer, the outer regions of its crust are being pulled off. But here's the crucial part. Those layers are being compressed. They're being forced inward. The material from the surface is adding to the mass of the neutron star. The neutron star is being packed down. It's being made denser. Think about what that means. A neutron star is already impossibly dense. A teaspoon weighs as much as all the cars on Earth. But now, more material is being added to it. More mass. The same gravity that's destroying the star is also making it heavier, making it denser, making it more extreme. This process has been happening for thousands of years, maybe millions of years. No one knows exactly how long the system has existed, but we know it's real because we can see it. In 1989, astronomers detected X-rays coming from V404 Cygni. These X-rays are produced by the superheated material in the accretion disk. They're coming from the edge of a black hole, produced by the friction and violence of matter falling toward infinity. And buried at the heart of that X-ray source is a neutron star being crushed and remade. Here's what makes this so hard to understand. Normal physics says this shouldn't happen. A neutron star should be torn apart by the tidal forces. The gravity near a black hole is so uneven, so much stronger on one side than the other, that it should rip apart everything in its path. It should tear the neutron star to shreds. But it doesn't. The neutron star's gravity is so strong, its self-gravity is so powerful, that it holds itself together even as the black hole tries to tear it apart. It's held together by something so extreme that we barely have the language for it. It's gravity, pulling inward, against gravity, pulling outward. And the neutron star wins. For now, The accretion disk around V404 Cygni is feeding material to the black hole at an enormous rate. That material came from somewhere. Most of it came from the companion star, the normal star that's also in this system. But some of it, increasingly, is coming from the neutron star itself. The neutron star is being consumed. But it's not going down without taking everything with it. As material falls from the neutron star into the black hole, it accelerates. It spirals. The friction creates jets of radiation that shoot out perpendicular to the accretion disk. These jets are not gentle. They're powered by gravity so extreme that they can reach speeds of 90% the speed of light. They're powered by matter falling into a place where space itself is being shattered. And the neutron star at the center of it all, the thing that refused to fully die, is still there, still intact, still being crushed into something more extreme, more impossible than anything else in this corner of the universe. This is where our understanding starts to break down. We know the neutron star is there. We can see the evidence in the X-ray data. We can see the jets. We can measure the effects of its gravity, but we don't fully understand what's happening to its interior. A neutron star is already so dense that normal physics doesn't apply. The laws of quantum mechanics and relativity are being pushed to their absolute limits. At the center of that neutron star, there might be something even more exotic than neutrons. There might be exotic matter, quark matter, something that only exists under conditions so extreme that we've never reproduced them on Earth, something that we can barely theorize about, let alone understand. And that something is being crushed even further by the black hole's gravity. The distance between the neutron star and the black hole in V404 Cygni is about 31 million kilometers. That sounds far. But in cosmic terms, it's close. Dangerously close. It's close enough that the gravitational pull of the black hole is warping the neutron star's shape. It's being elongated, stretched slightly on the side facing the black hole. Every moment, the neutron star moves slightly closer. The orbital decay is slow, not immediate, but it's happening. Given enough time, in millions or billions of years, the neutron star will spiral into the black hole. And when that happens, when one of the universe's most extreme objects finally falls into another, something will happen that we can't fully predict. For now, the neutron star clings to its existence at the edge of the abyss. It refuses to disappear. It refuses to be forgotten. It continues to pull in material from the companion star. It continues to feed the black hole while being fed by it. It's locked in a dance with infinity itself, and it's being crushed into something new. We live on a world that feels stable, solid, permanent. The ground beneath your feet has existed for 4.5 billion years. The sun that warms your face has been burning for 4.6 billion years. The stars in the night sky have been there since before humans existed. They feel like permanent fixtures of the universe. But they're not. Everything is changing. Everything is dying. And in that death, something new is always being created. The neutron star orbiting V404 Cygni is dying. It's being consumed. But it's not being destroyed. It's being transformed. Its matter is being crushed into something denser, something more fundamental. It's being forced into conditions so extreme that we don't even know what forms matter can take there. And that transformation is happening because of gravity. The same force that keeps you on the ground. The same force that holds planets in orbit around the Sunday. The same force that makes stars burn for billions of years. The same force that created you. Because the iron in your blood came from a star that exploded millions of years ago. Gravity is not gentle. It's not a background force that you can ignore. It's the fundamental truth about how matter behaves in this universe. It breaks things. It compresses them. It forces them together until they transform into something completely new. This has been happening since the universe began. In the first moments after the Big Bang, everything was compressed into something infinitely dense. Gravity pulled it all together. And when the universe expanded, gravity was there, pulling, compressing, trying to hold things together. Stars formed because gravity crushed hydrogen until it was so dense that the atoms couldn't resist anymore, they fused. Planets formed because gravity pulled rocks and dust together. Your body formed because gravity allowed things to stay stable long enough for life to emerge. And now, at the edge of a black hole, gravity is doing the same thing it's always done. It's crushing. It's compressing. It's transforming. The neutron star will eventually fall into the black hole. That's inevitable. The mathematics of orbital mechanics makes it certain. Not today, not next year, but eventually. And when it does, what happens? The neutron star will cross the event horizon, the boundary beyond which nothing can escape. Its material will fall toward the singularity at the center. And something will happen that we can't fully describe. The laws of physics as we know them break down. Space and time themselves become undefined. The matter of the neutron star will be transformed into something that exists beyond our current understanding of reality. But here's the thing that we don't talk about enough. We don't actually know what happens there. We have equations. We have theories. We have mathematics that works for almost everything else in the universe. But the very center of a black hole remains unknown. It remains a mystery. And in that mystery is something profound. The universe still has secrets. Even after centuries of science, even after we've measured galaxies billions of light years away, even after we've split atoms and sent probes to the edge of the solar system, the universe still has a core of mystery. A place where our understanding simply stops. And that place is both terrifying and beautiful. We built our understanding of the universe because we looked up at the night sky and asked questions. We wanted to know what those lights were, why they moved the way they moved, where we came from, what we were made of. And the answers we found were more strange, more wonderful, more profound than anything we could have imagined. We're made of atoms forged in the cores of stars. Those stars exploded. That material drifted through space for millions of years. It collided with other material. It formed the Earth. It formed the oceans. And then, somehow, it woke up. It became conscious. It became you. And now, you're looking back up at the stars, wondering about them again. That's what makes this story so important. Not just because there's a neutron star being crushed at the edge of a black hole, but because it reminds us of what we are. We are made of the same matter that forms these extreme objects. The carbon in your bones, the oxygen in your lungs, the iron in your blood. All of it came from stars. All of it was forged under conditions of extreme heat and pressure. All of it is the product of gravity-crushing matter until it becomes something new. And we're asking about it. We're studying it. We're building observatories and sending telescopes into space to understand it. Even though we're infinitesimally small compared to these objects, even though we exist for only a blink of cosmic time, we're trying to understand the universe we're part of. The neutron star at V404 Cygni is being crushed into something new. It's being transformed by the most extreme forces in the universe. And in 1 billion years, or 10 billion years, it will cross into a black hole and disappear from our universe entirely. But for now, it endures. It persists. It continues to shine in X-rays that our telescopes can detect. It continues to pull in material and feed the black hole. It continues to exist at the absolute edge of what's possible for matter. And we know it's there. We can see it. We can study it. We can slowly, patiently, build our understanding of what's happening. That's enough, because the universe doesn't need us to understand it. It doesn't care if we know the equations that describe it. It follows its laws, whether we're watching or not, whether we're here or not, whether we exist or not. But we do exist, and we do care. And there's something profound in that small fact. The stars will burn out. The galaxies will drift apart. Entropy will increase until everything is cold and dark. But for this moment, this tiny, insignificant moment in cosmic time, matter has arranged itself in a way that can observe the universe. That can ask questions. That can be amazed by the mystery of it all. And somewhere out there, in the direction of Cygnus, a neutron star is being crushed into something new. And if you have a telescope, and you point it in the right direction, and you're patient enough, you might see a faint X-ray source. And that light is coming from the edge of a black hole. That light is telling you a story about what's happening there. The story of something that refused to fully die. The story of matter being forced into the deepest extremes the universe can create. The story of survival and transformation, and the silent, incomprehensible power of gravity. And that story is still being written.